All right, Unit 14, the last unit of the year. And this is just a brief introduction to calculus. And I know this whole course is called Pre-Calculus, and it's getting our algebra skills ready to go into calculus. But what calculus is, it's actually a study of a couple of concepts that we've learned in algebra, like slope. A big part of calculus is the study of slope. But we're going to start off real basic, and we've got this crazy notation here. And the first section, if you're heading on to calculus next year, the first section that you're going to study is called limits. And limits are what happens as a function approaches a number. And it's just this notation right here. So I would read this as the limit as x approaches some number of a function, and that would equal some number. And we'll get a little bit more familiar with this in a bit. So the first way we're going to look at this is through a table. And I've created some tables on here, and I've created some tables on Desmos that I'm going to show you, and I'll show you how to make a table on Desmos. But here it says to find the limit using a table of the limit as x approaches 3 of 5x squared. So 5x squared is our function. And if I were to put a table and I pick some x values, now we want the limit as x approaches 3. So I have 3 in my table. And I could plug that in here and have 3 squared is 9 times 5 is 45. Okay, so pretty simple. But what we want is what's happening to the numbers that are very small distances away from 45. So I've created this table. 2.99 is close to 3. 3.001 is close to 3, just a little smidget more than 3. 3.01 is a little bit farther away than this. 3.1 is a little bit more. But these values, and these are approaching in from lowest to highest. So if I start with 2.9, then 2.99, I'm getting closer to 3. And then when I get to 3, I get a little bit farther away and a little bit more farther away with these next values. So I created a table on Desmos, and again, I'm going to show you how to make the table. And I'm going to try and zoom in here. Here's our function, 5x squared. And here are those values that I put in here, and we're getting numbers that are close to 45. If I plug in 2.9, I have 42.05. Then if I get closer to 3, I'm getting closer to 45. If I go a little bit more than 3, I have a little bit more than 45. And the farther I get away from 3, I get numbers farther away from 45. All right, so I would plug in, if I were you, I would write those values in this table. I'm just not going to take the time to do that right now. So we can just see that if I plug in values into the function that are close to 3, I get numbers out that are close to 45. Now, a lot of times when I'm finding the limit, I can just plug in the value and it's going to give me an answer. All right, so if I plug in this case, I'm going to zoom back out. If I plug in 3, I get 45. But in this next example, if I plug in 2 into the function, because this is asking us to find the value of the limit as x approaches 2 of this function. So if I plug in 2, I have 2 squared minus 4 over 2 minus 2. And I get a 0 on the bottom. I get actually a 0 on the top. So we don't know what this is. All right, so what I'm going to do is I'm going to, in my table, look at what's happening to the numbers that are close to 2. All right, because 2 is where I want to find my limit. As x approaches 2, what's happening? Now, I have that also on my table. And again, this is just Desmos. I'll show you in a second how this works. But in this one, we just said before, if we plug in 2, we get undefined. But what's happening to those numbers that are very close to 2? And if I look here and I put numbers starting here at 1.9, 1.99, I'm getting close to 2. And then a little bit more than 2, 2.001, 2.01, 2.1. Okay, so if I look at these, 3.9, 3.99, 2 is still undefined, but here I have 4. So if I were to pick a number to put in here between 3.99 and 4.001, I would probably choose 4. All right, so in this case, the limit as x approaches 2, even though the value is undefined, those values around 2 are getting closer and closer to 4. All right, so that's what a limit is. So in this case, I would write that as the limit of x approaches, as x approaches 2 of our function. I'm not going to write out the whole function. In this case is 4, because these numbers, as I showed in the table, are getting close to 4. All right, so this is how this works in terms of getting this on Desmos. Now, in this case, in this right here, I just have the function put in for the next example. If I want to change this to a table, I'm just going to go up to this little wheel thing right here, and I'm going to touch it. And next to x plus 2, this is the function, and I can change this to a table. So I'm just going to touch that, and it gives me a table. All right, so that's how that worked. And if you can see, they will pre-choose numbers for you, and you can see their pre-chosen numbers give you points that are in a line here. So this is just kind of like a scatter plot of this table. But these are not the values that I want in my table. All right, so I want, as the limit of x approaches 2, I want those numbers that are really close to 2, like 1.9, 1.99. So these are the numbers that I have to change in here for x. And by the way, to get those dots to go away, I can just touch this and the graph goes away. Okay, but here I want these values in for x. So I'm just going to delete what's here and type over them. So I want 1.9, and then I want to delete, I want 1.99, and then I want 2, and then I want 2.001, and then I want 2.101, and then in the next one, there's nothing there, I just tap down, I want 2.1. Okay, so these are my x values, plug into the equation, and I get this set of y values out. Now, if I were to plug in 2, so if I wanted to just find the limit of the function as x approaches 2. That's how I would say that. The limit of the function as x approaches 2. Whoops. I can just plug in 2. 2 plus 2 is 4. Now, if you notice, these numbers are the same numbers that we had up here. Okay, these numbers are the same. And this is why. Okay, so I have the same f of x values. Now, if I were to take this function, let's just come down here. And how about if I factor that? So I have the limit of x as x approaches 2 of x squared minus 4 over x minus 2. So I can factor this part right here. So this would give me x plus 2 and x minus 2. And on the bottom, I have an x minus 2. And if we cancel those out, these are really the same function. All right, so when we were studying polynomials, remember, if we have a continuous function, okay, and this is a continuous function, I can just plug the value of 2 in, and 2 plus 2 is 4. That would be my limit. But sometimes I can't plug the value in. If I plug in 2 here, we noticed I got the 0 denominator. So I'm not able to find the limit by just plugging in 2. So that's when we were looking at the tables here, and we were able to see that as x is approaching 2 from either side, from either numbers less than 2 or numbers more than 2, we were getting closer and closer to 4 in both of these instances. All right. So the next one on the next page has this, and this is a common limit in calculus, very common. You'll see that a lot. But we want to find the limit as x approaches 0 of sine of x over x. Now, we can also look at that on a graph. All right, so I'm going to bring this back, and down here, I have this function plugged in, sine of x over x. Right now, my graph is not visible, so I'm going to, oops, touching in the wrong place. I'm going to make my graph visible, and I can see, whoops, those are from before. I can see what's happening here as the numbers are getting closer and closer to 0, because that's what my limit is asking. As x approaches 0, what is happening in the graph? So this is what my graph looks like. Let's just draw a picture of this graph. So it's kind of going up here, hitting 1, and then going back here. So this is the graph, and it looks like at 0, 0, I have the value of 1. And I'm just going to refer back to this again one last time. And we can see in my graph that as I go towards 1 from the left, and I go towards 1, and this is an x value of 0. So if I go towards 0 from the left and towards 0 from the right, it looks like I have a value of 1. But we know that if we put 0 in for the x value, I have a denominator of 0, so that's not going to work. And I can actually see if maybe I can find an x value of 0. Ah, there we go. So if I have x is 0, we can see that it's undefined. So the value of the function at 0 is undefined, but the limit as x approaches 0 from both sides is heading towards 1. So that would be the limit. So as we head towards 0, we're getting a value of 1. But there's actually a hole in this. Remember when we talked about rational functions, we have holes, okay? There's a hole there, and the value would be undefined, but the limit is 1. All right, so in example 5, it says to find the limit by graphing the function, find the limit of x approaches 2 of f of x. So let's just graph this. This is a piecewise function, and we did these early on. So it says if x does not equal 2, this is our graph. All right, so 3x minus 2. So here's a minus 2, up 3 over 1. So this is what our graph looks like here, but not at 2. We're going to have a hole there. At 2, the x value is 3. So over 2, up 3. So this is what this graph looks like. So if I wanted to find the value of f of 2, that's the exact value. That means if x is 2, y has to be 3. But the limit as x approaches 2 of the function, and again, this is what's happening as x is getting closer and closer to 2. So here I'm getting closer and closer to this number, which would be 4. Okay. Last example. Here we have a function, f of x is x if x is less than 0 or equal to 0. So at 0, I have a dot, and then it's just f of x equals x. So -1, -1, -2, -2. This is f of y equals x line. Then if x is greater than 2, the value is going to be 1. So this is just going to be a horizontal line at 1. And x is greater than 2, so it's going to start here at 2, open circle, and go this way. All right, so in this graph, if I plug in what x equals here, the value of the function at x equals 0 falls here, and that would just be, would be 0 at f of x equals 0. At x equals 0, the value of the function is 0. But if I look what's happening from going this way to going this way it's heading towards 0. This way, there are no x values that are close to 0 here. So in this case, it is no limit. Okay, and what happens here, I'm going to make a note here. If the graphs are discontinuous, or if you see breaks. And are not approaching the same value from left to right, the limit doesn't exist. And the big, if the limit doesn't exist, the big abbreviation does not exist, instead of writing all that out. So if you're finding the limit of this value at 0 and you're not connected on both sides of 0, then you don't have a limit. Okay, so you got some practicing to do, couple on a table, couple with the graphs. Do the best with your practicing, and we're going to talk about this some more algebraically in section 2.